Yeah.
All right. Thanks for coming. Let me go ahead and get started. My name is Jian-Xun Wang. I'm professor here in mechanical engineering. So if I introduce your speaker, I want to tell you a little bit about the story. That happens in 2016. I was still assistant professor. I was invited to attend the NSF review panel. It's a career award review, and so it's usually to review the junior faculty, the proposals, and it's considered to be a prestigious award for NSF. So after the panel, faculties got together, start complaining about the difficulty hiring students, right? I'm sure if it's a robotics seminar, this entire room might be filled with people, but now it's been challenging getting students to work on the hydraulic fluid mechanics. Then, 2016, I think that was a year AlphaGo was out. AlphaGo, be the lead zero, I think in earlier that year. So that triggered a lot of interest on deep learning, right? So faculties were complaining. Now students are all going to AI, going to robotics. How am I going to be able to get students? Then there happened to be one person. He's actually a chair of the Virginia Tech. And he was saying, we get some faculty that actually applying AI to turbulence. So right after he said that, quite a few people raised their eyebrows in the room. These are big names in turbulence. I don't want to share with you the detailed information. I'm not supposed to. People were surprised. People were kind of stunned. Machine learning is generally considered a black box, right? When you apply to turbulence, we have well-defined equation, Navier-Stokes equation that describe how fluid moves. Is this a right approach? A lot of people casted doubts on this, right? But shortly after that, there is a boom of research applying AIs to study fluid mechanics and turbulence. Right, this is probably the most popular area in the past decade in the field of fluid mechanics. If you look at the papers, the number of papers published, number of citations gained by these papers. So today it's my pleasure to be able to bring the experts who was at the forefront of that newly established area in the field of fluid mechanics. The person that the Virginia Tech chair referred to was his advisor, and he was the first student of that person. As you can imagine, student is usually the person who does most of the work. Now, I think I'm pretty confident to say that you are the person who's actually really pushing this field forward and has done a tremendous amount of work applying the AI to understand the flow to eventually model the flow. And Dr. Wang, Jian-Xun Wang from the Notre Dame, and he got his PhD from 2017 from Virginia Tech, and shortly after got a faculty position in 2018. Has been very productive in the field, and based on his citations, based on the influence he has made. So with no further ado, the floor is yours.
Thank you, Darren. That's a very kind introduction, and thank you for inviting me here. So I'm very happy to have this opportunity to share with you guys some of our research. As you know, my research expertise is in the scientific machine learning, data-driven modeling, and computational mechanics. So I'm really interested in how can we integrate the data and into the computational models and using advanced data science and scientific machine learning techniques, and to enable better predictive modeling for different complex systems. So today, I'm going to share with you some of our recent development along this line, which is a physics integrated differentiable neural modeling framework to model or emulate different spatial temporal physics. So as we know that like the simulation, computational modeling and simulation capability plays an essential role in for us to understand, predict and control complex systems like aerodynamic flows, flow structure interactions, and turbine machineries or like cardiovascular biomechanics systems, where we're interested in like modeling the manufacturing process of the carbon composites, which gonna involve like complex chemical reactions and coupled with heat transfers. You can see all of the system, they have shown the spatial temporal behavior, and to simulate the spatial temporal physics. And usually we need the governing equations, right? And those governing equations are a set of partial differential equations. And to obtain the solution of those system of PDE, and we need finite volume, finite difference, finite element, those numerical method, and to solve, discretize and solve those PDE system. And this is a traditional way how we model and simulate the system. So they have been very successful, but they also face certain challenges in certain scenarios. For example, if you are trying to deal with a very complex system, sometimes the complete governing equations, reliable model forms may not be fully known. This is due to either our limited understanding of all the underlying physics. So there might be some like constitutive laws and some part of physics that we don't understand. Or in some cases, even though we know the governing equations, it's not feasible to resolve everything. For example, turbulence. We know the turbulence is governed by Navier-Stokes. But the problem is you cannot resolve all the scale down to common growth for any arbitrary high Reynolds numbers. It's just not feasible. So people develop the closure models and as SGS models. So those closure terms or closure relations, we don't know the reliable like model form for that. So in general, the complete model form may not be fully known. And in many scenarios, like even we know the governing equations in many cases, the modeling input, like the initial boundary conditions and the mature property, like the model coefficient or physical parameters could be unknown or uncertain. This is pretty common in many biological systems, like it will simulate the patient-specific like system that mature property across different patients could be different. So how to measure the mature property in vivo, that's very hard. So like the modeling input could be uncertain. And most importantly, like I said, in many cases, the traditional computational models, usually they are very expensive and it make it not feasible for the real-time applications for digital twins, for like the applications that requires many model queries, for example, to do like design optimizations, solving inverse problem, or propagate uncertainties, like doing uncertainty quantifications. So the recent advances in AI and GPU computing, combined with ever increased the data availability from the experiment, from the hypertest simulations, actually open up the new opportunity for us to tackle those challenges. And by developing the data assisted or data enabled computational model. This is a very broad field, but I want to talk about the data-driven like surrogate model today, because you can see in this field like there's a growing like research interest in this area. For example, in the past few years, we have seen a lot of work, like people develop the data-driven models data-driven surrogate models or reduced order models to emulate different spatial temporal physics using deep learning, deep neural networks. So one of the example is Mesh GraphNet, and which is developed by DeepMind, I think 2 years ago, and they have shown like the state-of-the-art performance for emulating different spatial temporal physics like structure dynamics and some fluid structure interactions, and also some simple aerodynamics and hydrodynamics like the periodic vortex flow shedding or vortex flow. So visually, they look pretty impressive. But if you check out the underlying modeling structures, it's actually quite simple. So what they did is they just built a message passing deep graph neural network to capture the transition of the state from the current step and to the next one, completely from data. Okay, so once this model is trained, And we can use this model by providing the initial conditions and auto-regressively evaluate these models, and you can doing this model rollout and to emulate the spatial temporal physics, okay? So I call this type of model is like a purely data-driven next step neural predictor. So from the numerical perspective, this is more like we're doing the explicit time stepping, but the thing is this time stepping is actually learned from data instead of derived from the Gaussian equation and numerical scheme you use, right? So one issue of this model is you can imagine the error could be accumulated during this process. And this error accumulation could make the long-term prediction not robust. So here I'm showing you like the mesh graph and predictions. And after a long-term model rollout, after like 250 seconds, and for this periodic vortex shedding, visually it looks pretty physical. But if you compare with a CFD reference, you can see after a long-term prediction, the phase is actually opposite. It's completely opposite. And here we plot the drag coefficient histories. So starting from like the initial condition, doing the transition and go to the steady state, the vortex sheddings. And you can see compared to the reference, there is a notable discrepancy, meaning that the phase is not accurate, but still like the magnitude is pretty good. But this is a relatively simple flow because it's quite like periodic. So if we move to a little bit more complex vortex dynamics, like this one is channel, and you have a jet at inlet, the angle could change over time. So it will create a little bit more complicated dynamics, still not turbulent. So in this case, you can see at the beginning it can capture this dynamic pretty well, but you can notice like it becomes noisy, and eventually it becomes completely unphysical because the prediction is dominated by the accumulated error. This is the error accumulation I'm talking about. And so you can imagine like the poor robustness for the long-term, long-range predictions is pretty common for this type of model, especially when you try to emulate the dynamics becomes more chaotic and turbulent. So another issue of this data-driven model is the generalizability. So if you test it for a different initial condition, different like new parameters, different viscosity Reynolds numbers and boundary conditions, the performance is not guaranteed. And this is pretty common for any data-driven model. So how to improve the generalizability in the out-of-training regimes. So how can we improve? Okay, so from the deep learning community, we can improve this next step learning structures. It's not ideal to capture long-term dynamics. And in the NLP community, people have spent a year to develop a better sequence model to capture the long-term dynamics. Definitely we can do that, okay? Design a better sequence model. And another issue is so far everything is completely based on data, but for us, we have a lot of knowledge about the system. We try to model the fluid, we know the Navier-Stokes, and for different heat transfer, we know the some physical laws. So how can we leverage those physics? But those physics could be, only partial. So I'm going to talk about this in the next few slides. So let's first talk about this, the simple improvement, which is from the deep learning side. Okay, in the NLP, the natural language processing community, people have spent years to develop the more advanced sequence models, from the simple recurrent neural networks and to LSTM, GRU, and to the latest like transformer with attention mechanism. And they have shown like they can better capture the coherence in words, coherence about the words in long sentences. Okay, so basically the attention mechanism is the core of the success of the recent large language model like ChatGPT. Okay, so basically we can improve this next step learning structures by integrating those advanced sequence models, and we actually built this attention mechanism and to improve the mesh graph net. And this is a collaboration with DMITE, I think in 2022. So the idea is we use the graph massive passing to do this mesh reduced dimension reductions, and in the latent space, and we use a temporal attention mechanism to capture the long-term dynamics, and this is more like a temporal transformer, and we thus improve the performance. And so here we test. Oops. We test our model. Okay, we test our model for on-C Reynolds numbers and start from like the initial condition and try to capture the transition to the steady state vortex shadings. And you can see like the pressure field and velocity field and agree with reference pretty well. And if you look at the drag coefficient histories, and this time the blue line, which is CFD reference, and dashed line is our transformer-based graph, match graph net. So it agrees with each other much better than the original match graph net, which you can clearly see the discrepancies and the phase arrows. But this still is a very simple flow, the periodic vortex shading. So if we tested it for a more complicated flow, like this is a 2D LES for this backward facing step. We just want to test like this little bit chaotic flows and test it on two different on-C Reynolds number, 5,000 to like 50,000. And you can see like at very short term, it still can capture the dynamics, but for the long term, the performance is not still satisfactory because when the flow becomes more chaotic and unstable, the error accumulation still exists, and for long term, the prediction is bad. All right, so everything so far is completely based on data. And we know that we have we are not completely blind to the system. We try two models, right? So we always have some applied knowledge about the underlying physics, even though, like I mentioned, those underlying physics are most of the time they're kind of vague, uncertain, and incomplete. Because, for example, we know like the general backbone physics, the conservation laws, but there is a lot of like constitutive relations and closed remodeling relations, and some part of physics we don't fully understood. So there's some missing part. So how can we leverage this incomplete and vague physics to enable a better data-driven model? So when people think about physics-informed learning, I think most people would think of like the physics-informed neural network or PIN, which has been very popular in the past 2 years. And our group, we also kind of be one of those groups like to develop PIN. But the PIN, the idea is quite simple. If you have a complete governing equation or physical laws, and you can use that to actually regularize the neural network training by integrating the residual of the governing equation into the loss function. So then you can penalize the violation of the physical law, and so that you don't need to rely too much on the label data. So this is a general idea. But think of this approach. So basically, most of the time we kind of treat those constraints as soft constraints, and it will make the training more difficult because you have many different terms in the loss terms, and you're actually doing this multi-objective optimization that will make the training much more difficult. And most importantly, here we're talking about the scenarios that we only have the partial physics. The governing equations may not be complete, and you have some governing equations, but you don't know the complete model form. So it's not possible to even formulate the physics-informed laws since the complete, like the equation residual form is not completely known. So here I would like to introduce a different perspective of utilizing the physics. Here we propose to integrate the partial null physics in the form of the PD operators like convection, diffusions, gradient, as a part of the neural network architectures. So the rationale behind this is actually the relationship between the numerical PD operators and neural network architecture components. So to give you some concrete ideas, I will give you some examples. Like if you know like the neural network, so the ResNet is very popular, very successful. So the building block for the ResNet is the residual connection layers. So if you look at the mathematical formulation of the residual connections, it is nothing but a Euler description of certain ODEs. So on the other hand, if you use the ODE and to define the residual connections, and it actually a residual connection with infinite number of layers if it's continuous. So by leveraging this relationship in deep learning, people have developed like the residual ResNet with infinite depths using the ODE, solving the ODE, use adjoint. So basically, this is known as the neural ODE. And similarly for convolution, which is essential for any convolution neural networks. So the convolution operations can be interpreted as the finite difference space, the spatial differentiation operations. So based on this, and you can actually bridge the convolution operators with spatial PD operators on the uniform grid. And this relation can be extended to unstructured non-uniform grid by linking the graph kernel, a convolution kernel, or massive passing with the finite volume-based spatial differentiations. And there are other examples like sequence network structures and has a relation to the controlled differential equations. And also the recurrent, if you see like recurrent neural networks, recurrent structures can be interpreted as the implicit time-stepping scheme. So basically, based on this relation between the PD and neural networks, we try to encode some of the no PD operator into the neural network as a part of the architecture. So let's go back to our problem. We try to build a sequence model because we know like sequence model is better to capture spatial temporal physics. And how do we build this sequence model? Because we know this physics is governed by system PDEs, but for this governing PDEs, we only partially know this. So it has a null portion and unknown portion. So the coupling between a null physics and unknown physics could be another unknown nonlinear functionals and with also some unknown physical parameters. Okay, so now let's build this sequence net. So here I just put a generic recurrent neural networks. Okay, so to define this Rn, and we have to define the recurrent network unit, which is basically to describe the state from t to t+1. And here we don't want to completely based on black box RAS connections, convolution RAS connections. Instead, we kind of use the relation between this convolution and residual connections and to actually encode like the PD operators in the null portion of the physics as a part of the non-trainable comp residual connections, and couple with the trainable comp connections, and it can couple with nonlinear REST connection blocks, and we to redefine this REST block. Okay, so now we have this kind of PD encoded recurrent neural network unit, and we can use that as a building block to construct more fancy like the sequence net, like the LSTM or TRU as we want. So this is just a general idea, and how to decide this block is kind of problem dependent, and I will showcase some design later in the next few slides. So this is like the physics integrated neural models, and to encode some incomplete physics as a part of the neural network architectures. So this is in contrast to PIN because we're not actually modifying the loss function, but the neural network structures. So here I'm going to use this idea to simulate like the fluid flows. So for example, we want to build a sequence model, still like data-driven model, and we try to learn the fluid dynamics. So basically the dynamics about the velocity and pressures. Okay, so when we define this recurrent learning unit, and we actually refer to the Navier-Stokes. So we have the 3 blocks to redefine the convolution residual connections, and you have the convection, component diffusion, and pressure projections. So all the blue parts are the trainable conv residual blocks, and we also can add this conv residual block, which is predefined by the PD operators like convection, diffusion, and you put them together based on the right-hand side of Navier-Stokes, and you redefine this conv residual blocks and to define this transitions. Okay, so basically the t here, t to t plus 1 delta t is much greater than the numerical delta t because we want to build a surrogate reduced order model which has a faster inference speed, and we have everything operating on the coarse resolution. So the solver going to be very fast, and you can use that to reconstruct the LSTM. So the time stepping is no longer the numerical time stepping. So you have the hidden state and the calorie memory. Okay, so you also can add like the SR, the super resolution component, which is trainable to recover like the high frequency, high wave number details. So this is very flexible. So here, before we actually construct the sequence model, and let's see if we bring this kind of physics and can this improve our learning capabilities. So let's just use this one learning unit to construct the next step model. And we compare it with the mesh net, which have the same structure, but everything is black box, and you have the same amount of trainable parameters. And let's see if we can improve the performance. Let's still like look at the previous case, this 2D vortex flows, and we train our PD integrated models and compare with the black box baseline. Okay, the first row is reference, and we tested on 2 on-C Reynolds number, 3,000, a little bit higher, like 10,000, and also the jet position could change to different locations. And again, both data-driven models, they can capture the dynamics at the beginning, but after a while, you can see the difference, especially like for this black box model, and the prediction becomes wrong and noisy, and especially when the Reynolds number is higher and completely like off from the reference. So this is more clear if you look at arrow propagation figure. So the horizontal is model evolution step. So how many model rollout you perform, and this is relative arrows. So this one is purely black box, and the blue one is our PD integrated. And the scattering represent the robustness of model because we tested the model for different Reynolds numbers. So for some testing, they may have lower errors, some they have even higher errors. So the scattering is huge, and the scattering can be significantly reduced, and the error accumulation problems can be significantly improved by doing this. This is just the one step. Okay, we just use this one learning unit and to develop like explicit Euler time stepping. So as we know, like if we can use that to define like more fancy sequence network. So here I'm showing you like if we just use that learning blocks and to construct LSTM. So this is LSTM. You have the hidden state, you have the memories, and to carry on the memory. So numerically, we have some like more advanced time stepping, and more importantly here, the loss function is not Peter forcing. So the loss it can based on the entire simulated trajectories, and you can optimize the entire sequence models and based on the entire trajectories. So in this case, you have to make sure that everything is differentiable, so you can backpropagate the gradient over the entire sequence model. So everything is in the differentiable programming. So we code this using JAX, and which is fully differentiable. So you can train this end-to-end and sequence to sequence like LSTM, and it is completely on GPU. And this is the differentiable sequence model. And we can use this model to learn and predict the 2D forest, the homogeneous isotropic turbulence as a demo case. So the first column is the DNS from higher spatial temporal resolutions. And we want our data-driven reduced R model to work on very coarse mesh spatial temporal resolutions. So the spatially it's like 32 times greater, like in both X and Y direction, and temporal-wise is also 32 times larger in terms of time step. So in the second column and third column, we're comparing the results from the PD integrated and the purely black box. Okay, so the training, we actually use the data from 0, like normalized T to 800, and for training, and let's first see like if they can do the forecasting. Okay, so both the model can within training range, they're both good. And after like going to like forecasting, and you can see this noise. I think it's more clear to see this error propagation. So this green line is black box and blue line is our PD integrated. So you can clearly see like the error propagation, error accumulations, and it can be significantly reduced. So here we also show you like if we completely based on the PDE and the traditional physics-based closure. So here we actually do the LES. We have the SGS, and we completely solve the PD on this coarse mesh, no data at all. So it won't work because on such a coarse resolution, it doesn't work. So the error is huge at the very beginning. And now this is more like you simulate this from some like no conditions, and you just do the forecasting time. What about I randomly generate the initial condition and see how it works? So now we test all the models given a randomly generated initial condition. So this is just random field, and we start from random field, and then we do the forecasting and simulate it even for a longer time. So previously to like the 600, and now we simulate it even to like 2200. And again, the second row agree with the DS very well. But if you see like the pure data driven, like even the second row, they significantly deviate from the reference. So that is the generalizability, because purely data driven black box models, and it can work for the data like in the range that you have data, but if you completely from like the arbitrary initial boundary conditions, it won't work. So here I plot the energy spectrum for both models. So you can see the green and the yellow light, they're almost identical, but the green light, you can see for most of the wave numbers, there's a big discrepancies. So similar idea can be applied to solving the flow structure interaction, because this FSI problem is very costly most of the time, and we want to develop the faster efficient surrogate model for that. So again, we can construct this physics integrated LSTM. And so basically, I don't want to go into too much detail, but the idea is just you, instead of construct the black box, you have integrate the governing equation for the fluid and structures. So the interaction between fluid and structures is based on the immersed boundary, which a lot of like the part can be trainable. So you can think this is like a hybrid neural solver, but it's fully vectorized, fully differentiable, and so it can leverage GPU computing, and also can be trained like a deep LSTM. So we test this model on like the two a standard benchmark FSI problem, vortex-induced vibration, and the flow past the like flexible B. So you can see here I'm showing you this vortex-induced vibrations. So the ground truth is from the high fidelity FSI simulations, and if you we want to develop like the gas surrogate, so we have pretty coarse spatial temporal resolutions. And for our neural solver, it can capture dynamics, but if you completely like rely on PD and solve it, assuming you know the PDE, right? For this case, so it won't work basically on such a coarse resolution. And you can clearly see like the solid mechanics, the structural dynamics is completely wrong. And also I apply the displacement for this three models. So for data driven, because we have data, of course, we can improve this. So here I'm showing you like the black box and with the PD integrated data driven models. So both can capture the displacement, the overall the magnitude, but you can see a lot of the details. The purely black box models cannot capture, especially in this displacement spectrum. So let's go to the flow field. So in this case, I'm showing you like the ground truth PD integrated neural solver and purely black box data driven black box models and pure solver. So the training window, you still need some training data, right? So the training window is from normalized T from 0 to 15, and it refers to see the forecasting. So in this case, if you compare like the neural solver and pure data driven, and within the training, you have data. So both models they are pretty good, but going to the forecast range, and you can already see some noise, maybe not very clear in the screen, but here I'm plotting the arrow. Like, so when it go to this forecasting range, this this green line going up, that because of our accumulations, and this can be largely reduced. Again, the pure solver, I mean, on the coarse resolution won't work. So you may think, okay, it seems that we can basically use the neural network to kind of improve the pure solver, like the PD solver. What about like we train a neural network to learn the discrepancy and use the neural network as a correction and plug that back to the PD solver, right? This is some traditional like way to couple this ML models with a PD solver, like the data-driven turbulence model, but it is not stable. I call it weakly coupled, and this the stability issues have been also like see in the data-driven turbulence models. Okay, so this is like we do the forecasting time. So start from like the no initial conditions, and also like the training spring stiffness. So what if we change the spring stiffness? Okay, so if we change the spring stiffness to a different values, and in this case, we completely like test on unseized spring stiffness. And in this case, you can see the purely black box model, they fail, even at very like for short term, they cannot predict the dynamics at all. This is because of generalizability. But PD integrated neural solver, again, they can capture the physics pretty well. And this can be also see from this arrow propagation figure. At the very beginning, this green curve is going up. Okay, so for this case, the structural dynamics, basically, they just diverge. All right, so for the second case, I think I don't want to go into detail, I can deliver a similar message. So I will skip this and to directly talk about the computational cost. So for this two-dimensional FSI problem, so the inference cost of this trained hyperneural solver for a single learning step is about 20% of the numerical solver on the phi grade for one numerical step. Because here, one learning step can cover multiple numerical steps, so we still have a pretty notable speed up for long span predictions. And because this 2D FSI, the high-fidelity solver is not that expensive, but it still have like 8 times speed up compared to the purely numerical GN solvers. But here I want to mention that this pure solver, no matter it's on the phi or coarse grade, they are all GPU accelerated solver. So we developed this like PD solvers, which is fully vectorized and running on GPU. So it's already like a vectorized Jack solver. So it's already much faster than the traditional solver if you use the Legends code on the CPUs. So I'm talking about speed up compared to this GPU solver. If the baseline numerical solver is on the CPU, and like you use an open fault, the speed up could be much more significant. And the cost of the training model, we use single GPU is comparable to conducting a single high fidelity simulations. Remember, we can, once this is trained, and we can parametrically do the simulation. So we can enjoy the speed up of the parametric and multi-query, many-query applications. So in the last few minutes, I would like to talk about another very important aspect of this framework, which is uncertainty quantification. Because you can see this differentiable neural modeling frameworks like platform allow you to simulate the data and with partial node knowledge and and also numerical models and put them together and to build a predictive model. So we would expect uncertainty could from different sources. So for example, if you have training data is from measurement, and you could have a measurement noise, and that will bring the data uncertainty. And also, usually we expect that we introduce a physics and we would only need a very sparse data. So the data sparsity would introduce uncertainty because for the region you have data, you're more confident about more model. And for the region you don't have data, you are less confident. So how do we consider the data sparsity and to convert it to the UQ? And also we integrate the physics, right? The partial physics, and those physics, sometimes they're not 100% precise, and we can introduce a model uncertainty. And also we have a lot of physical parameters, which is uncertain or unknown, and it will introduce parameter uncertainty. And lastly, we have the neural networks, deep learning, and it has the uncertainty due to the potential over-parameterization of the neural networks. Right. So we can group those uncertainty to two classes. So one is aleatoric uncertainty, which correspond to the uncertainty which is due to the intrinsic randomness. So this cannot be reducible. And also epistemic uncertainty, which is due to the lack of knowledge. So if you introduce more data, more information, this uncertainty can be reduced. So now the question is, how can we quantify and estimate uncertainty in this framework? So to extend this to the probabilistic formulation, and we need to formulate our state. So the state predicted by the models, and as random spatial temporal variables. So the goal is we try to find this predicted state, and given the input of your model, like boundary condition, initial, and also the training data. So this is the goal that we try to compute, which is the conditional probability of the state. Okay, so to compute this conditional probability, and you need to marginalize the posterior distribution of your trainable parameter theta. Maybe I should first introduce the notation. So here the x tilde represent the input to the model, including like coordinate, initial condition, boundary condition, and no physical parameters. And theta here represent all the trainable parameters, including like neural network weights and bias, and also the unknown physical parameters, everything you want to optimize. Okay. And here the D represent the data, the training data. So basically, we want to characterize the conditional probability of your state, and given data and given the input, right? So this can be computed by marginalize the posterior distributions. So usually, we need use Monte Carlo who can randomly sample the posterior distribution of your trainable parameters. So now the problem is solved. Of course not. This is gradually. We can do it in this way, but there's still many challenges. First one is, how do I model the likelihood functions, like model predictions, and given the input and given the parameters, how to model this? And the second one is, how do you practically sample the posterior? So this is not trivial. The theta could have a million dimensions. That's a very high dimension problem. So the traditional inference, Bayesian inference won't work. And how do we propagate uncertainty over those linear and nonlinear PD operators within this differentiable neural model framework? So let's first look at the modeling of likelihood functions. So basically, we can model define the measurement models, and which is stated. So your measurement, which is a conditional probability of B and even x tilde and theta, can be defined as a mean and also like a zero mean multivariate Gaussian noise. And based on this measurement model, you can describe this conditional probability as a multivariate Gaussian. Okay, so now we can change our differentiable neural model, the output. We can model distribution instead of the deterministic predictions. So now the output of the model is actually distributions, because we have the Gaussian assumption that you can actually model the mean and covariance matrix as the output. Okay, so try to train this model if we don't consider the theta, the uncertainty from the trainable parameters, and we can actually maximize the likelihood. So the likelihood can be computed by the product of this Gaussian multivariate Gaussian density. So training is like minimize the loss, which is the negative log likelihood. Okay, so in this way, you can see if you take the log of this equation and you actually minimize the data mismatch MSE, but at the same time you maximize the variance and try to match the data uncertainty. So in this way, the training process allows you to model and quantify the uncertainty arise from the data noise. But all the trainable parameter theta only have a point MLE or MAP estimate. So we actually don't actually consider uncertainty from the theta. So that's why I call it this part as aleatoric UQ. So you actually quantify the uncertainty, aleatoric uncertainty, data uncertainty. So the second question is, how do we quantify the epistemic uncertainty, which is from the trainable parameters? So in this case, you have to sample the posterior. Like I said, directly computing the posterior from the traditional Bayesian sampling techniques like MCMC or HMC is infeasible due to the high dimensionality of zeta. And it's going to be very slow convergence, just cannot, it's not visible. Additionally, because we have neural networks usually present very complex posterior landscape, and this method are very struggle to navigate this landscape. So here I mean just show you like one-dimensional zeta, and this illustrated figures I'm trying to show like the complex the posterior landscape is a multi-model. Okay, so how do we approximate this posterior instead of like actually doing the Bayesian sampling? So the idea is based on the recent study that people have empirically find out like the stochastic gradient descent with a constant rate can this stochastic gradient descent iterate can locally approximate the loss landscape. So basically we use this idea and we can initialize multiple SGD trajectories. So you actually do this training and with multiple stochastic gradient descent with the different initial conditions, and each of them will locally approximate the geometry of the posterior, and we use the Gaussian and to fit that local posterior geometries, and we use the model average, which is a Gaussian mixture model, to capture the non-Gaussian posterior landscape. So in this way, we can actually approximate the geometry of the posterior. So now we have the aleatoric and epistemic uncertainty to be quantified, and then we can redefine our probabilistic differential neural models. And lastly, we also need to probability uncertainty through this linear and nonlinear function. So usually one of the primary metric is to express uncertainty is a variance or covariance, right? You define the confidence intervals. So basically you want to probably the first and second moment of the distribution within this solver. So here, if the operator is linear and this mean and variance covariance can be derived analytically based on the applied transformation. But if it's a nonlinear, you have two ways. One is, okay, let's just do the Monte Carlo capture the nonlinear transformations, but this is too costly. So here we choose the unscinded transform and to define the sigma points and to more effectively propagate the mean and variance across the nonlinear operators. So here in the last 5 minutes, let me show you some validation case. So the first case, we have the Hamiltonian system. That's a 2D ODE. It's pretty simple. The dimension is low, so we can actually verify our UQ approach. So for this hybrid model, let's just simply define the right-hand side of the equation. ODE for X1 is a neural network, and the second one is the null equations. And then we basically collect some data. So for X1 and X2, the data noise level is different. So you can clearly see like the observation for X1 is less accurate. You have more scattering, and X2, you have like more precise measurement. The data noise is lower. And then you train this model, and the model can basically make the prediction, like do the forecasting. At the same time, it can quantify the aleatoric uncertainty and epistemic uncertainty. You can see the aleatoric uncertainty, which is data uncertainty. It can reflect the noise level, right? So for this one, the data uncertainty is higher than the X2. And the epistemic uncertainty is also reasonable because when you go to like the extrapolation range, the uncertainty grows. So combine them is the total UQ, and we compare this result and with the MCMC approach. Because this is a low dimensional problem, we can do accurate Bayesian sampling. We use HMC and to do this UQ, and this shade, the blue shaded area is MCMC, and this orange one is our approach. So they align, which is under very well. So it's kind of like a validation of this UQ. And then we can tested on a PD problem. This is a reaction diffusion equations. And we still have a two-dimensional and two spatial temporal variables. And for the reaction terms, we don't know that we model it as the neural operators. And the training, we collect some data, and only for the second state variables, the V2. And then we train this model, and the model can not only inference or like do the forecasting for V1 because we have no data for V1, and then also it can do the forecasting for V2. And the first row is the ground truth, second row is our predictions, and it basically captures this. The mean is accurate, but we also have errors. But we are interested about our like confidence of the model, which is reflected by the uncertainty, which is correlated with your prediction errors, right? And here I choose the three like representative locations and plot the predictions and with uncertainty. And you can clearly see like within the data, uncertainty is low, and if you go to extrapolation range, uncertainty grows a lot because this epistemic uncertainty is very high for this case. So this is like the demo, but in the last 2 minutes, let me show you the some real world applications. So this is one of the project that I was working with Air Force R and Honeywell. So they are interested in like modeling the manufacturing process of the composite, carbon-carbon composite. So they want to optimize their manufacturing process so they can optimize the material property that can be used for hypersonic applications. But if you, like Honeywell, they will do this like try and error, and it really take months to finish this manufacturing process, or even a year. So that's going to be impossible. So the goal is to develop a model. Okay, so the here I just show like one of the process, which is known as chemical vapor infiltration, the CVI process, because this is the main process Honeywell to manufacture the carbon-carbon composite. So the chemical vapor infiltration, you can think of it, we have the porous, like the preform, and we put that into this reaction chamber, this oven, and we inject the gas, reactive gas, and to grow the carbon on this porous mediums and to densify these materials. And so that involves some multi-scale, multi-physics, heat transfer, and also the chemical reaction. So here is a possible chemical reaction with a lot of species just for one recipe. So it has many different recipes. So basically, this system is a complex system. It's not practical to or infeasible to model such a multi-scale, multi-physics process purely based on physics. And because the reason is the physics is not fully understood, and the computational is going to be infeasible to resolve all the physics and all the scales. So long story too short, we just try to extract the backbone physics, okay, which is actually a diffusion and reaction and deposition. Okay, so we can aggregate all the species and we use the effect of like a diffusion coefficient and reaction rate. But all of those like reaction, porosity, and diffusion, they are spatial temporal field. So basically we use, so for example, the diffusion coefficient is going to be a spatial temporal field, and it is related to like porosity field. It's another spatial temporal field, temperature and pressures. So the mapping between those fields are unknown. We don't know that, especially this is like effective diffusion coefficient field. So mapping between two functions are operators. So we use the neural operators to define this relation. It's similar for the reaction rate and deposition rate. Okay, so we can use this backbone physics and to construct the sequence model and use this neural field and basically hybrid those neural field into, you can think this is differentiable numerical solvers, and we can construct the sequence model. Okay, so basically, a sequence model will describe the dynamics of the molarity, which is the gas concentration field, and porosity and temperature over time. Okay, and but the good thing is we don't need to have the training data for any of those like porosity or density. We can only measure the total mass of your sample. This is doable in the manufacturing process because in this manufacturing process, like Honeywell can take out the sample from oven and measure weight and put it back. And after a while, like cook it and then take it out and get another measurement. So here we first use the synthetic data, try to mimic this process. So we basically do this CVI process and take this sample out and cut it to 3 pieces and measure weights for each pieces. So we got this mass data and across this manufacturing process. So because it's densification, so the mass is growing up. And because it's a synthetic data, so we have the synthetic ground truth, and we're going to use this to train our neural differentiable models. And first, we can make sure that our model prediction mean actually can reproduce the data we have. And in this case, the model uncertainty can barely see. There's almost like no uncertainty because we are observing this variables. But more interestingly, we can also like infer those hidden state, which is spatial temporal field. So here I choose like the 2 representative locations, center and corner, and we plot the dynamics of the diffusion coefficient field and the molarity and deposition and porosity. And especially we're interested in the porosity because it's related to the material property that we want to optimize. Okay, so you can see for diffusion coefficient that the solid line is our model mean and the dashed line is ground truth. So there are some discrepancy, but this time your model, the estimated uncertainty is also large. And for the porosity, and you can see there is still like some discrepancy, but the good thing is we want to be confident about our model like within the uncertainty range. So that's why we need this UQ capability. And this is just for one case. We're interested in like many different like operating conditions. So our model is not just like the traditional model software. For one operating condition, you need to simulate it once. But the good thing of the neural network is you can parameterize. So for different temperature and different partial pressures, this is like 2 parameters to define operating conditions. And we can actually collect the data from some of the training conditions, like Honeywell is doing that, and we can basically test it on like those unknown conditions. Some of them is within your training range, and some of them could be like out of the training range. It's more like extrapolations. So here I'm showing you the predictions, and this is for the porosity. I still like, because it's spatial temporal field, it's hard to visualize, so I choose the 2 representative locations. You can see like within the training range, the prediction is pretty good and uncertainty low. And out of this training range, it's more like generalized to the testing conditions. You can clearly see like now the mean prediction is less accurate, but our uncertainty is large. So that is what we expect from this model, right? So if we can collect a little bit more data and want to see if that prediction can be improved. So we still tested those uncertainty conditions, and you can see this time uncertainty can be significantly reduced and accuracy can be improved. So this is like the synthetic data. We also tested on like the real data. This is like real data, 2 experiments. The total pressure is 20 kPa and 100 kPa. And so basically there's like different operating conditions. The partial pressure is like 10, 20, and 50. So this dots are the weights, the data we use to train this model. And for the training conditions, like the 50, 20, and 10, or 15, 8, or 5, you can see like it can reproduce the data. So, but the uncertainty increases when you don't have data. And this is a real experiment data. And we also want to test it for some unseen partial pressure, like the unseen operating conditions. So those are like the here the dot are not used for training, only for comparison. So you can see for both experiment and the prediction agree with the reference pretty well, but it is interesting because you can see if this partial pressure is 30 or 50, which is kind of within my training range, actually the prediction is very accurate, okay? And uncertainty is very low. But if like our prediction is quite out of my training range, 100 kPa, so our data is also less. So in this case, you have like large uncertainty, but the trend can be captured. So this is an example I want to share with you guys. I think almost use all the time. So I will stop here, and I'm happy to take any questions. All right.
Out of time, but let's see if there are any questions from the audience. Okay.
Just an understanding question. So, my understanding is that when you are putting the PDE into the neural network, you
Yes.
are actually proposing also the physics of the system. Is that right? Or
So we kind of incorporate those physics as a form of the PD operators. Like if you know like Navier-Stokes, right? So you can actually encode the convection diffusion pressure gradient and into a network. And when you build a network, you can based on the partial differential equation, you know. And for this case, basically, this is the example like we don't know the complete governing equations. We just know, okay, there's a diffusion and there's the reactions. There's a lot of terms that we don't know, the 100, like the species and the chemical reactions. So those are handled by the neural network, but learn from data. So this is like, but everything is differentiable. So you can think this is like neural networks, or you can think this is a numerical solver, but with the neural network like integrated in the numerical solver, but the numerical solver is implemented in a way like a neural network, and it's fully differentiable, and you can be trained like a neural network. So yeah.
but okay, but my question is okay. All right. So if you are proposing in a way the physics by this neural network mechanism, so how do you validate? Like you are showing some ground truth, like because that's probably done with some established physical model, but then you are proposing another physics model, but then
Yeah, if
you get agreements. So I'm confused, like how if this makes sense or not.
Yeah, so for example, like for the real world, for the like the synthetic case, so it depends on like for the fluid, we actually know the physics. The problem cannot resolve all of them. So if you have a computational resource, you can do DS and you know the ground truths. So the goal is to actually develop the surrogate, make it solver faster. So in this case,
Right.
you can validate your surrogate if it's accurate or not. You can do like the DS, right? But for this case, yeah, real world, you actually don't know the underlying physics, and you don't have the high fidelity models. So in this case, we first use the like the synthetic, generate synthetic data, which is kind of assume like a model. And this model may not be accurate, but we just assume, okay, this model generated the synthetic data, and we can validate our algorithm. But for the real case, the only way you can validate this model is do the experiment and actually measure the hidden state you cannot measure. And for some cases, you can basically validate your model. That makes sense.
Yeah. But I think on the slide, on one slide, I forgot the number, you are actually showing a validation, like a ground truth. So I was
that is for like I validate the UQ. So that is no system, like the Hamiltonian system. That is no. So we just assume like we don't know part of it. So this is actually no. So that's a synthetic validation. Yes.
So I was wondering, like, since you have all these like partial differential operators that kind of a known, and then you have trainable, can you discover kind of like what the important operators are?
Yes,
and
that's
fluids, there's different regions where like maybe it's like Stokes flow and
that's a really good question. Actually, I didn't show that direction. So this is also our interest though, because we can establish like the relation between like convolution and the PD operator. So yes, you can actually discover like what PDE you actually can be learned from the data. And we have another direction, which is like the equation discovery. So in the equation discovery, there are so many different approaches. Like Cindy, they have a library of the terms, and you basically do the sparse regression and try to impose the sparsity and get the most Passmonian form. And there's like the so-called like this PD net, and yeah, you can you can also like infer like the PD operators in the discrete form and with some constraints. And there's other ways like so-called symbolic AI. So it's like a symbolic regression. So you define the operators like the multiplications, additions, subtraction, differentiations. So use a Monte Carlo train and to construct those terms and with operators. And so you try to optimize this and to find like one train. So this can be done by reinforcement learning. And we have another paper talking about that. So you can actually discover the governing equations in that way. Yeah. But here, what I'm showing today is more like try to improve the black box surrogate model. So people have developed this model, just want to predict the physics. And the goal here is not really like to discover the analytical form, but that is another important direction.
Thank you.
Chris?
A question on how much training is needed, and then after a model is trained, can you extrapolate it to different geometries, or let's say it was a gas flow and we're changing the gas, so the viscosity as a function of temperature changes. Do you need to retrain for all of these circumstances, or do you feel comfortable extrapolating?
That's depend, right? So it depends on how you construct this hybrid models. So if your physics can basically take in the boundary conditions like the geometries, you don't need to retrain. But if your geometry is input of your neural network, then you need to retrain. So basically the part you learn is geometry dependent or not. So for example, like for the fluid case that I didn't show like a specific application. So we are doing like turbulence. So we try to model like the wall boundary turbulence. So basically we know like some small scale turbulence is less geometry dependent, and large eddies are geometry dependent. So we actually use this core solver and to simulate the large structure geometries, and we use the generated model like diffusion model and to generate the small scale turbulence. And that small scale turbulence is believed to be like a less geometry dependent. So basically in that way, we don't need to retrain, because like in a common group scale, like the turbulence is universal for different geometries. So for the large eddies, we still want to simulate it from solver perspective. So we can do this. But if you make everything like black box, yes, you have to retrain, or you have to parameterize geometry, and you can do some interpolation between these geometries. And when the prediction is way like far from the geometry you see during training, and it will fail, right?
Here's a question.
How do you include your unknown physics to your architecture?
So how do I integrate unknown physics to that? So the goal is we want to learn it from data. So if you're unknown, so you don't want to integrate any structures, but you want your flexibility. Neural network has the flexibility to learn unknown physics.
But you don't have the right hand side.
So the formulation is we assume that we know something on the right hand side. If you completely know nothing about the right hand side, that means you completely blind to the physics, and if you only have data, that you no choice, you just need to use the data to train it. So that becomes a neural OD. So you know this is like a continuous dynamics, and you can define du dt and equals to neural networks, and that is a neural OD or neural PD. So it's a deep learning model. So you can use that to basically impose some smoothness, and that is, so when you use the data, basically if you use the data with different time intervals, and in this approach you can still train your models. I think the performance is better than the convolution LSTM or sequential convolution LSTM, because it's fixed delta t. But well, that's if you know nothing about physics, then yeah, you have to rely on data. That's
good. Yeah, very impressive work. So I have many questions, but let's just pick one. So for your UQ part, you basically assume Gaussian form such that you can reduce the number of sampling. Right?
Oh, it's actually has two parts.
Yeah.
The first part is to quantify the data uncertainty. So we just assume like the measurement has a Gaussian distribution. So the measurement noise has a Gaussian distribution.
Okay.
But for the posterior, we didn't assume Gaussian. We actually use so basically we use the stochastic gradient descent to extract to explore the very complex posterior geometry multi-model. So each SGD trajectory explore one local geometry, and we use the Gaussian mixture. So if you mix the multiple Gaussian, it becomes definitely multi-model. So it's a like non-Gaussian. So we're actually not limited to the Gaussian. So if everything, you can assume everything is Gaussian, and you can do the variational inference and just make your neural network to predict the mean and variance, and you can use the variational inference because it's a exponential family. So the variational inference is very effective. But here we try to avoid assume that the posterior is Gaussian.
So do you, when you do UQ compared to just do prediction, do you need more training, or is it still the same amount of training? And
Its training data is the same, but the overhead is you need to initialize multiple training because I need multiple like SGD. So usually we need like 8 or 10. So but it can be in parallel. So it can be there's no communications between those SGD trajectories. So the goal is because in the deep learning, if usually you do like train neural network, you will like start from different initial conditions, and sometimes it will convert to a different local minimum. So we want a systematic way to find all the good local minimum or global minimum. So you are not like, so you're more confident about to explore the entire posterior landscape instead of like track to one maybe bad local minimum. So
you're not using this surrogate model to do more sampling and to quantify the UQ. It's still from the original training data.
Right, still from our new training data. Yes.
All right, great. If there's no other questions, let's give our speaker another round of applause.
I know. Said that one that just look at yeah, that's right.
Why is so low?
It's no training. I just come early.
You have
training pause. This new coaching. Come back. So there's no training.
So that's what you have to do bars.
And because when you run the software, it's not training, it's an inference. So when you run it, you evaluate the training,
Okay.
and also you run the training. Yeah.
And you said you can use much larger time step size like that because so I'm wondering, so in this system we don't need to follow sequential computing or anything like that.
Yeah, that's
why you can.
because we're not using the traditional numerical time stacking. So
But I mean, say even neural ODE or whatever, there must be some constraints.
yeah, that's true.
What is that? Yeah.
Definitely you can about like the CF.
So is it because it's similar to say implicit time integration such as? So
Implicit, because you have the memory.
implicit. Okay.
Yeah, you have the memory, so it's not like traditional like solver because it's a LSTM. So LSTM you carry the memory like from the previous. So when you have the memory, it's not like a stick to like the explicit weight or cool down. So yeah.
Okay, great.
I'm John Nichols.
Yeah.
Nice to meet you. Yeah, I know, I do like papers on like CFD and hydrodynamic stability analysis.
Yeah.
Transition. On complex thick flows, I like doing like adjoint
Oh, right.
dynamic simulations.
Yeah,
I know.
This was recorded.
Oh.
Your
Okay.
discussion.
Yeah. So I just